Many FEA analysis packages cannot predict the effects of load stiffening when attempting to avoid potentially destructive responses to vibration. Load stiffening occurs when an object, such as this guitar string, is stretched to produce a specific frequency or tone. For example, as I loosen or tighten the string, its tone or natural frequencies will change. In an airplane or car, loads or forces, and therefore natural frequencies are constantly changing. Therefore, to predict the dynamic response, you must consider load stiffening. ALGOR offers two ways to predict frequencies as a result of load stiffening. The first way is with the vibration level 2 extender. First, we measure the force applied to produce this low A note, or a natural frequency of 110 cycles per second, or hertz. Multiplying the measured force with a leverage factor of 220 for the screw gives us an applied tension of 31 pounds. Then we measure and weigh the string to obtain its mass density. Also, we need to measure the cross-section area of the part of the string which will be in tension. Now we can plug the data we have gathered into the load stiffening module, which predicts the first vibration mode at 110 hertz. The correct result. Note that the second mode is one musical octave higher at 220 hertz, and so on up the musical scale. AccuPack Nonlinear Analysis Extender is the second way to predict frequencies as a result of load stiffening. Note that when the A string is twanged, complicated waveforms appear. Notice that there appears to be waves within the wave of the string, and that the outer envelope of the mode shape itself seems to have waves. These waveforms result from the bass frequency combining with the other frequencies within the string. For the AccuPack analysis, we will twang the string at a typical spot which would occur during actual playing. Notice the tension force and the boundary conditions. Looking at a plot of the position of the center node versus time, we can get the bass frequency by counting the peaks. Here we have approximately 11 peaks over 0.1 second, or 110 hertz, which agrees with the previous calculation. Note the higher frequencies coming in here, and lower frequencies, or beating, showing up in the waveform envelope. Beating is often responsible for the low frequency growling sounds you sometimes hear in airplane cabins. Plotting the node which was twanged, the higher frequencies are even more evident. Counting the largest and second largest peaks together, we get the second octave 220 hertz, and so on up the musical scale. Finally, let's look at the visual response of the string as predicted by AccuPack. It is this complicated response that causes a simple string to produce a rich tone. You need software that can predict the effect of load stiffening so that your designs can produce music to your ears.